Today I'm going to go through the calculations behind the Earth Curvature Calculator. The Earth Curvature Calculator is a web page where you can calculate the target hidden height based on your distance to the target and the eye height you are at. So when you see here, I put in my eye height is 11.7 meters. It is 34.9 kilometers to the target. Then 40.4 meters at the target should be hidden because of the Earth curvature. This is a drawing of the Earth. So here we have the Earth's center, we have the Earth's radius, and we are standing on this point, and our eyes are at this level, h0 above the ground. And we are looking at our target, which is h1, which is here, and this h1 here is the target hidden height. This distance, or this part of the thing we're looking at, should be hidden by the Earth's curvature. And we have d0, which is the distance from us to the target. To calculate the target hidden height, we need to use Pythagoras and equations. According to Pythagoras, in a right-angled triangle, the square of the hypotenuse, this line here, the x, which is the side opposite the right angle, this is a right angle of 90 degrees, is equal to the sum of the squares of the other two sides, this side and this side. So x squared, the hypotenuse squared, equals the first side squared plus the second side squared. So we can calculate this. If we want to find x here, we can calculate 3 squared is 3 times 3, 4 squared is 4 times 4, 3 times 3 is 9, 4 times 4 is 16, and 9 plus 16 is 25. So now we have x squared is 25, and we want to find x. So that means that x is the square root of 25, because the square root of a number is when you want to find the number that's squared with itself is your result. So we want to find what number that will multiplied by itself be 25. Then we use the square root. In this case it is 5, because 5 times 5 is 25. So in this triangle, x, the length of the hypotenuse, is 5. Our problem with the target hidden height can be reduced to 2 triangles and 2 right-angled triangles. That means that we can use Pythagoras to calculate our problem. So here you see the first triangle is this triangle here. So one side here is r, the Earth radius. This side is r plus our eye height, which is h0. And we have d1, which we don't know, which is part of the distance to our target. So here we have r, the radius of the Earth. We have r here plus our height, our eye height, which is h0. And we see this part to the target. The next triangle will be the same type of logic. We have the radius of the Earth, we have the radius of the Earth here, and we have the target hidden height here, which is h1. And we have d2 here, which is the distance to the horizon the other way. So we have these two triangles. And we want to find h1, which is the target hidden height, and we want to find it as a function of the other known parameters. So all the other parameters here are known. R is the radius of the Earth, and d0 is d1 plus d2. d0 is this whole distance, the distance to our target, and h0 is our eye height. So as we said, the total distance to the target, D0, is D1 plus D2 together. We don't know how large these ones are, we just know that D1 plus D2 equals the total distance to our target. And we can use Pythagoras on the first triangle. So the hypotenuse squared equals one side squared plus the other side squared. We can do this on the second triangle as well. So there the hypotenuse is r plus h1. So r plus h1 squared equals d2 squared plus r squared. So now we have three equations with three unknowns. And that's an easy problem to solve. So we start by finding an expression for h1, which is the target hidden height and the thing we ultimately want to find. So we use the equation from the second triangle. We take the square root on both sides. So on the left side we have r plus h1 left. On the right side we have the square root of everything on the right side left. Then we can solve this on h1. So we move r over. So r on the left side will be minus r on the right side since it's moving side. So now we have an expression for h1, which is h1 equals the square root of d2 squared plus r squared minus r. We know r, but we don't know d2, so we have to calculate a bit more. We know that d0, which is the total distance to our target, is the sum of d1 plus d2. We can then find d2 as equal to d0, the total distance, minus d1. So according to the first triangle, the r plus ho squared equals d1 squared plus r squared. This is the Pythagoras. We can solve this on d1 squared, just moving it over. And we have d1 is the square root of this whole right side. Now we have an expression for d1 as well. And we know that d2 is d0 minus d1. So that means that d2 is equals to d0 minus the expression we just found. So that means we now have an expression for h1 that includes r, which we know, and d2, which we don't know. But we have calculated an expression for d2 with d0, which is the target distance, which we do know, r, which is the radius we know, and h0, which is the eye height we also know. So we can simplify the d2 equation a little bit. We just basically calculate this r plus h0 squared. So the r squared will disappear. And we're left with this equation, d0 minus the square root of 2r h0 plus h0 squared. So now we can substitute d2 in the third equation on this page. We can substitute d2 and we get this equation. So this equation is the equation for the target hidden height with only our known parameters. Here we have d0, which is the distance to our target. We have r, which is the radius of the Earth. We have h0, which is our eye height. So we know everything, and we can use this equation to find the target hidden height. So according to the Earth curvature calculator, the target hidden height for distance at 34.9 kilometers with the eye height of 11.7 meters is 40.4 meters. So we use the equation we found in the last page, and we substitute our distances. So here I've substituted d0, which is the target distance. We have to use only one unit, so we're using meters, so that will be 34,900 meters. I've substituted HO for the eye height, which was 11.7 meters, and R is here the Earth's radius, which is, according to Wikipedia, 6,371,010 meters on average. So when I also substitute the R in the equation, it will look like this. And I can calculate further by calculating what is inside the square root. And I can take also the square root of that number, of the first square root. So now I've calculated this value and I've taken this square root. I end up with this. So now I calculate what is inside this square root here, and this is the R. No, not changed. And I calculate the square root of what is inside the square root and withdraw the radius, and I end up with a target hidden height of 40.4048 meters. So my calculation is about 0.1 millimeter off from the Earth curvature calculator. That's very little, but it can be caused by some rounding error somewhere. Anyway, we see that the Earth curvature calculator is calculating correctly. So at a distance of about 35 kilometers, and I'm standing 11.7 meter over the water, I should not be able to see 40.4 meters above the water at my target. But the problem is, when I go out and take picture with my Nikon P900 super zoom camera, I don't see any curvature. So where is it? So click on the right to see what I actually saw when I took pictures across a lake 35 kilometers away when my eye height was 11.7 meters. Click on the video to the right to see.